Surely by now you know you should not applaud before the talk. You only regret that. Listen, it's a real pleasure to be back here at Spacefest. I'm going to try and address at least the question that has already come up. Why do we think they're out there? A little bit about what we're looking for. And I hope to challenge you by throwing out some, if you will, wild ideas about how we might look for ET, and then finish up with my usual screed about what it is we're going to find. I do some consulting for Hollywood films, actually, sci-fi films, not the ones that I would actually know something about. And they only ask 3 questions in Hollywood to me. They ask, why are the aliens here? Because they're usually here. Secondly, what weapons do they have? This is a fantastic question. That'd be like asking Julius Caesar, right? What weapons do you think the U.S. military will have in 2014? Big spears. And the third question they ask is, what do they look like? That one I will actually address, because of course we know that. All right, so here we go. Look, why we think they're out there. You've already alluded to it. It's because, in fact, our astronomical situation is hardly special. This is just a night sky, a view of the Milky Way, something you will never see from Colorado Boulevard. But, in fact, what we've learned in the past 2 years, and this is something new, right? That is that most stars have planets. We've heard that in talks. Mike has already told you about that. We've heard that in several talks. Most stars. In fact, I used to ask Jeff Marcy every 6 months. He's a planet hunter. And I say, Jeff, if you had perfect instruments, what fraction of stars would show planets? And he would say, I don't know, 70%, 80%. And I point out to you that for an astronomer, 70 or 80% is the same as all. In astronomy, pi is equal to 1. Okay, so that means, and because, planets are like kittens, you don't get just one, you get a bunch. So that means the number of planets in the Milky Way is on the order of 1 trillion. All right, now it's 1 trillion. And sure, most of those are going to be worthless, but if you buy 1 trillion lottery tickets, they're not all worthless. Okay. So fundamentally, that's the argument. There are also other sort of ancillary arguments that I won't go into, but this is a photo I made a couple of years ago down in Australia, actually in the northwest corner of Australia, the Pilbara Hills, and you can see, maybe you can see these round things here that look like fossilized cauliflowers. They're not. These are, in fact, stromatolites. These are the remains of bacterial colonies. We know the age of this rock to within about 2%. It's roughly 3.5 billion years old. So within 1 billion years after the Earth was born, it was already carpeted with biology. It didn't take life very long to get started here. That's maybe an important point. Unfortunately, the sample size is 1, so you can't be sure that it's important, but it is suggestive. It's very suggestive that life is, when you have a worldwide experiment going on, you get the chemistry that produces life quickly. So the idea that they might be out there, that's not a new idea, that's a very old idea, but being able to look for it is a somewhat new idea. This is the 85-foot antenna in lovely, glamorous Greenbank, West Virginia. And in 1960, Frank Drake, shown here in a photo that's time invariant, because Frank never changes. What's Frank? He's 84 now. And, this is good news and bad news, that he never changes. The good news is, he's 84 and he still looks like he did when he was 30. The bad news is when he was 30, of course, he looked like he was 84. But still. Okay, so Frank used this antenna, pointed at a couple of nearby stars in the hope of finding signals that would betray the existence of other beings. So that was the start of modern SETI, and that's more than a half century ago. As a consequence, there are people who think the fact that we haven't found anybody, and I got the question here in the hall, have you found him? Always an intriguing question. Look, if we found him, do you think I'd be at Spacefest? I'd be in Stockholm having dinner with a king, collecting a check. So, obviously, we haven't found him. But, some people read into that something significant. You haven't found him. More than half a century, you haven't found him. There's nothing to be read into that, except for the fact that SETI is underfunded, because the number of star systems that have been looked at carefully is very tiny compared to the tally of planets in the galaxy. Let me point out something else here. Is SETI a science? Well, I think it's a science, but it's not science in the usual sense, where you have an hypothesis and then you try and falsify it and that sort of thing. You can't falsify. We ought to point the antennas. And of course, the Kepler Space Telescope, which has been the subject of several talks here at Spacefest, has given us some indication. The mission of Kepler, its job, its mission, should it choose to accept it, was to find out what fraction of sun-like stars have planets that could be habitable. And it's sort of zeroing in on that. I mean, it requires some more data reduction because those turn out to be the very planets that are hardest to find. A lot of data reduction. This is a graph from the Planetary Habitability lab down at the University of Puerto Rico, actually. They put out this graphic. It's always up to date. This one is not so up to date. This is from the end of last year, so this is 5 months out of date. But you can already see here, they're on the order of, I don't know, 24 worlds that have been found already. Not very many of these by Kepler, by the way, that were in the star's habitable zone. In other words, water doesn't freeze, water doesn't boil. The problem is most of these are much bigger than the Earth. And if you have a planet that's much bigger than the Earth, it might not be great for habitation, because it might be like Neptune, right? So that was the situation then. This was something else that was announced, more or less at the same time as that last slide, a little earlier, in October. These were results based on preliminary examination of Kepler data by some groups at Berkeley and elsewhere. And they said, you know, looking at the Kepler data, it looks like about 1 out of 5 stars like the Sun have a planet like the Earth in the habitable zone. That's an astounding result, 1 in 5. I mean, it could have been 1 in 5 million. It's not. It's a sizable percentage. Okay, if 1 out of 5 lottery tickets won the Powerball, you know, that'd be great. Okay, and then red dwarf stars. Now I have here 16%, right? And, you know, Mr. Jonah here, Mike has already told you that this number could be 53%. That the answer depends on whom you ask. But again, this is a sizable fraction of red dwarf stars, which nobody had ever considered were great habitats for Klingons, might have a planet that could be habitable, and if you look at enough habitable planets, maybe you'll find something that's inhabited. So the number of Earths, if you will, cousins of Earth in our galaxy, is on the order of tens of billions. Okay, so for the 2 people in the audience who think, you know, tens of billions of other Earths just in our galaxy, forget the 150 billion other galaxies we can see, that they're all sterile, or they don't have anything intelligent. You have to admire those 2 guys, because they are very audacious. That means you are a miracle. Okay, I know you like to think you're a miracle because your mom's been telling you that for a long time, but it may not be true. Okay, here's the Island Telescope Array. This is up about 800 miles from where you're sitting in the Cascades. There are 42 antennas there, each about 6 meters in diameter, and this is what we use at the SETI Institute, where I work, to do our SETI experiments. You can go up and take a look at it, actually, during the week. It's open to the public. And, you know, what we have learned from these things I've just told you about, the high fraction of stars that might have planets, is that unlike in the past, where we would take a list of stars like the Sun and try and say, look, are these stars like the Sun? Do they not have a companion double that would ruin them for life? We would carefully select where we would point the antennas. Given that 1 out of 5, or maybe 1 out of 4 stars of essentially all interesting types might have a planet that could have ETs on them, we can just look at them all. We'll just look at the nearest ones. That's a real change. We can look everywhere now. Now here's my favorite idea, and that is to look at the red dwarfs. I already mentioned them. There's a picture of a red dwarf in case you haven't seen one. It's Proxima Centauri. It's in the Alpha Centauri system. It's the nearest one. I know it's unimpressive from far away. It's also unimpressive from up close, because red dwarfs, as you see, are kind of tiny little guys. They're the runts of the litter. They're the smallest kinds of stars. They only have a tiny fraction, 10% or less of the mass of the Sun, and very little luminosity. Now the consequence of that low luminosity, I mean these are really low lights, okay, is that they burn forever, essentially. I mean, they don't have much fuel because they're small, but they're like VW Beetles, right? VW Beetle doesn't have a very big gas tank, but on the other hand, it also has a very small engine. So it goes a long way on a tank of gas. And the consequence of this, and it's a simple computation, is that every red dwarf ever born since the Big Bang is still out there shining away. They're all in their adolescence. They're not even that old yet. Okay, so that means that they're old. It also is the case that there are a lot of them. Now, this is a photo I made about a week or 2 ago. Somebody who works at the SETI Institute, in fact, Lisa Quintana. And behind her on the big NASA hyperwall, I don't know what they use it for, watching movies, whatever. She was the leader of the team that found Kepler 186f. And I dare say most of you have heard about this. This was a big story in the news 2 or 3 weeks ago. This is the first Earth-sized world found in the habitable zone of its star. And Mike Conner has talked about that, others have talked about that. So, no, it wasn't you, Mike, it was somebody else, but I'll give you credit, there you go. All right, here are a few parameters about this thing. Because it's one of the Kepler candidates, it's far away, it's like 500 light years away. The Kepler stars are on average like 1,000 light years away, which makes it hard to follow up on these guys and try and find out, does it have an atmosphere, and this, does it have that? Now, of course, the question that we got at the SETI Institute was immediately, well, have you tried listening in this direction? And the answer to that is yes, we have. And for their part, the inhabitants of Kepler 186f were coy. We didn't get anything. And we looked from 1 to 10 gigahertz, too. We looked over a wide swath of the radio dot. That doesn't mean too much. Really, it doesn't mean anything. To begin with, maybe they were off the air, they were on vacation when we were listening. But beyond that, you have to keep in mind, you could have looked at the Earth for almost 4.5 billion years with your radio telescopes and not picked up anything. And it wasn't that the Earth was unsuitable for life or wasn't ever going to develop intelligent life. You just weren't looking in the last 70 years, right, when something was being leaked off the Earth. So the fact that one planet doesn't show anything, you wouldn't expect that. You wouldn't expect that. Now, the thing about Kepler 186f that's a little disquieting is that this is a habitable planet around a very dim star. So in order to be habitable, it has to be in a very tight orbit, which it is. You can see it goes around once every 130 days, and it does this around a dim star, a small star. So that means it's close in. And when you have one body orbiting another one close in, you get what's called tidally locked behavior. In other words, one side will end up more or less always facing the star. There are variations on this, but you can look at Mercury or Venus, they're somewhat tidally locked too. Moons of Jupiter, tidally locked, many of them. So, tidally locked would mean, in the extreme case, where it's like the moon, where one side of the moon is always facing you, right? Well, if this planet, Kepler 186f, is tidally locked, and one side's always facing the star, and the other side's always facing away, the problem is going to be, or at least it was thought to be, that on the back side, the dark side, it's going to get really cold. The atmosphere is going to freeze out, just pile up as snow on the ground. That's the end of the atmosphere. So it'll be one very, very hot side, one very, very cold side, no atmosphere. Forget it. It's dead, Jim. Okay? However, that was a very naive point of view. That was the point of view 20 years ago. But since then, scientists have been a little bit more sophisticated in the analysis and say, well, look, if there's really an atmosphere, then you're going to set up winds between the hot side and the cold side, and the winds will convect heat radiation outside. In fact, here's a fairly early model of one of these things, and you can see the temperatures are in centigrade, if you care about that. But the point is that, yeah, it's really toasty on the side facing the star. 50 degrees centigrade is pretty toasty. And on the back side, it's pretty cold. I don't know, I can't read the numbers here, but it's minus 30, 40 degrees centigrade as well. But there's some equatorial band, there's some region between sunlight and darkness where everything is hunky-dory, where the temperatures are just as salubrious as they are here in Pasadena. So even if it's tidally locked, it's probably okay. Here are two artist impressions. This one on the left is the one that NASA circulated of Kepler 186f, and it kind of looks like the Earth turned inside out. This is one I made in my garage with the flashlights and lampshades, and it shows that there's only a region in here that's habitable, so tidally locked. But in either case, Kepler 186 cannot be ruled out for life, even if it is tidally locked, and it's unclear whether it is. Now, I think we ought to look at more of these red dwarfs. Why? Not just because maybe 16 to 50% of them could have habitable worlds. I think they have other advantages. To begin with, 3 out of every 4 stars is a red dwarf. Right? It's just like nature in general. There are more small things than big things. Right? I think you go to Africa, you see some megafauna, or some African elephants, I don't know what. But there are a lot more field mice. So when it comes to stars, there are a lot more small ones than big ones. And since 3/4 of all stars are red dwarfs, if you only have enough money to say, look at, 10,000 nearby stars, if you look at red dwarfs instead of stars like the sun, on average, they're only half as far away, because there's just more of them. Okay? And if they're only half as far away, then the radio signal's 4 times stronger. All of that's got to be good news. Okay? the other thing is, well, I've already mentioned that, and I've already mentioned this, they are long-lived, they are older, and on average, they're billions of years older than the Earth. So this is one of the few instances I can think of where being older is actually better, because if you're older, there's been more time for you to develop the kind of sophisticated, complex, intelligent life that you think is what you are. Okay. All right, so red dwarfs would be an improvement on the traditional SETI strategy. I think we ought to do this. I'm not getting pushback on that. I just think we ought to do it. But anyway, here's another approach. This is just to provoke you mostly, since I don't seem to be provoking you in any other way. All right, and that is to forget about doing all these ordinary things and consider extraordinary things you might do. Let me point out to you that stars, and I already have, actually have a range of sizes, of course, but they also have a range of brightnesses. Now, this is a plot showing, bright stars versus dim stars. So here are the bright stars down at this end. There's the sun, and these are the dim stars, and this is just how many there are. There are a lot more dim stars than bright stars. It was like in 8th grade. There were a lot more dim students than bright students. And the kind of stars that really stand out at night, those stars, they're all the way over here. They're not even on the graph because the numbers are so low they couldn't get included in this graph. But those are the ones you see. Those are the ones you see. Here are some stars. Only 3 stars out of 1,000,000 are really bright O-type stars, the brightest of the bright. Okay. Those are the guys on the right. We're a G-type star, for those of you who don't know, the sun. So you see how big it is physically. All right? But it turns out that when you make a star twice the mass, it isn't that the brightness just goes up by a factor of 2. The brightness goes up more or less as the 4th power of the mass. Okay? So, what is that? It's 16 times or whatever it is. So if you have these really big stars, they're 100,000 times brighter than the sun. So you can see them over a volume of space that's 30 million times greater than you can see stars like the sun. Well, you multiply those numbers together, and on the sky, when you go out at night and look at stars, these really bright guys ought to outnumber the ordinary stars, the ones like the sun or the red dwarfs, by 100 to 1. And in fact, they do. In fact, this is true. Here's, for your delectation, some old stars, but never mind. Okay. So these dominate the naked eye sky. In fact, of the 2 dozen brightest stars on the sky, every single one of them is a brighter star than the sun. You're not seeing suns up there when you look with your eyes. Okay? It's hard to see stars as dim as the sun, let alone the red dwarfs. They're very hard to see. So, okay, they stand out because they're a whole lot brighter than the other guys. So maybe this gives you a hint. Maybe the same is true of signals from aliens. Your average Klingon civilization may, be doing this and that or whatever, but maybe there's some super civilizations out there, fairly small in number, maybe only 1 in 100,000 or 1 in 1,000,000 are like that, but they might be so much more obvious that those are the guys to look for, okay? So how can you do that? How can you look for the most advanced societies? Well, you could do experiments like this. You've all heard of Dyson spheres, named after Rodney Dyson. Nobody laughs. Either unconscious or they don't know. I'm going to assume you don't know. Maybe unconscious. Hang on. A really advanced society would say, look, we need more energy than we're getting from, burning logs in the fireplace. We'll just surround our sun, our star, with solar cells. Now, having a solid shell like this doesn't actually work for dynamic reasons. But you could break this up into lots of pieces, and it would work. It's called a Dyson sphere or Dyson swarm. And then you beam that energy back to the Earth. Now, the amount of energy being put out by the sun is like 10 to the 26 watts, those of you who measured it this morning. And the amount of energy that humanity uses, everything, right? Everything from the power plants and your cars and your Wii and whatever, all that is like 10 to the 13 watts. So the difference is 13 orders of magnitude. We could get 10 trillion times more energy if we did this. Mind you, if we did that all the waste heat from the brake linings would, ruin Earth's environment, but we're doing it anyway. Okay, so the idea is that a really advanced society might be doing something like this. And the deal is that the outside of this is going to get a little bit warm, right? It's not 100% efficient. Some of the energy indeed gets turned into electricity that you beam down as microwaves or whatever to your planet. But for the rest of it, it's just getting warm on the outside. So the thing to do is to look for some stars that have too much infrared radiation coming out from their direction. because that could be a Dyson swarm around that star. A perfectly legitimate thing to do. There's a guy at Fermi Labs in Illinois who has been doing this. The difficulty with this idea is that there are other reasons why you might get too much infrared that have nothing to do with aliens. They just have to do with dust in the system. But, you know, this is an experiment you can conduct in the privacy of your own home by just pawing through infrared data. And maybe that's a good thing to do. Here's another idea. This is a proposal to build a Colossus telescope. I don't know why they call it Colossus. 74 meters in diameter mirror. And, but it's not a general purpose telescope. A telescope with a 74-meter mirror would be extraordinarily expensive. But this one is designed only to look at a tiny, tiny speck on the sky. Very small field of view, just to look at one star at a time, if you will. And then it turns out you can build it for only $700 million, which is pretty cheap. And the idea behind this telescope is one thing: to look in the direction of stars nearby and see if they're planets that are putting out too much infrared, because there's a hyper-civilization there, and that's the waste heat that they're pumping into space. I asked the guy who's, Jeff Kuhn, I think is his name, who's proposing this. I said, where are you going to get the $700 million? You know, we can't get 1% of that for doing SETI. And he said, private donations. So maybe some of you in the audience are going to build this. Here's another way. This is a distribution of the powers of radars we have here on Earth. So it's a logarithmic scale. So, you know, sort of 1 billion of effective watts, 10 billion effective watts, 100 billion, so forth. You can see that, you know, when radars are lower power, there are more of them, of course. But there are some radars that are very high effective powers. In other words, the amount of radiation they beam into space. And you can do that calculation. How far away can we see, for example, our television with our SETI experiments? And the answer to that is not very far. Not even as far as Alpha Centauri. But what you could see are radars. You could see the most powerful radars. You could find Jill Tarter and everybody. All my colleagues would get that question, when are we going to find it? And I thought it was a silly question when I first joined the SETI Institute. Who knows? Right? But I noticed that all my colleagues had an answer. They didn't say, who knows? What they said was, that'll be years and we'll find it. And so I sort of listened to all the answers, and it turned out that the answers correlated very well with the number of years until they were going to retire. So I thought, okay, maybe that's not a very good answer. Here's a better answer. You're looking for a needle in a haystack. Right? So the question is, when do you find a needle? Clearly, that depends on only three things. How big is the haystack, how fast you're going through the hay, and how many needles are in there. We know how big the haystack is. We're looking in our galaxy. We know from technology how fast we're going through the hay, and that's what this graph gives you. We're going through the hay faster and faster all the time. It's improving more or less exponentially following the growth in the capability of digital electronics. So the only thing you don't know, if you want to know when you're going to find a needle, is how many needles are in there. And we really don't know that. It could be zero. I mean, two people in the audience are thinking zero. And it might be. I mean, we don't know. But here's just some sort of graph showing, you know, how far out into the galaxy we can see as a function of time. But these are guesses for the number of needles. This is Carl Sagan's, for example. He figured there might be a million needles, in which case we might find ET fairly quickly. This is Frank Drake's. He figures only 10,000. It takes a little longer. Isaac Asimov figured 670,000. Asimov, being brighter probably than these other people, was able to do this to 2 decimal places. It's pretty good. All right, but really, if any of these guesses are even close, right? If these encompass the truth, or even if they don't, but they do within factors of 2 or 5, then this means that SETI, if we can continue doing it, is going to succeed while you're still around to read about it. Right? This is not something like building cathedrals in the Middle Ages, where it's going to take another 10 generations or something like that. If this is going to work, if this idea has merit, it's going to work while you're alive. Careful crossing this. Okay. All right, so that's my prediction always. And let me finish up this somewhat speculative talk, but that's always the main thing to say. What is it we're likely to hear? It's question number 3 that the Hollywood guys always ask. Are they going to look like these little gray guys and the big guys? No clothes, no names, no sense of humor, whatever. And I always point out, Lori Marino told me years ago, she said, Seth, this is just a prediction of what humans are going to be like in 1,000,000 years. Right? The only thing that get bigger with their eyes because they're all designing websites. So when you chow down on, the delicious repast here in the convention center, essentially 1/3 of all the calories are going to keep your brain warm. And this is irrespective of whether you're actually using it or you're just sitting in the audience here, sort of zoned out. So it's very expensive metabolically, by the way, which is obvious, and also the reason that most critters have opted not to have big brains. You can't really afford it metabolically. But in any case, this is what we assume we're like. This is the history of our brains over the last 3 million years, our predecessors and so on. 3 million years ago, our brains weighed half a kilo, so like 1 pound. 1 million years ago, our brains weighed 2 pounds, and today, your brain weighs 3 pounds. Now, the reason I show this graph is not to show you that, your brains have gotten bigger with time, but that maybe they'll continue to get bigger with time, and that's what ET has already done. So if you ask what are the aliens going to be like, hey, they're going to be guys with 10-pound brains. That's possible. It's clear that going from 2 to 3 was important, because if you have 2-pound brains, you're 4 state, and if you have 3-pound brains, you get a slot here. So that's the assumption, that there'll be bigger brains. But of course, that's probably wrong, and I say this every time because I really think that this is fundamentally wrong. We are in the century where not only are we understanding biology, I think we're going to find life in space, and a whole bunch of other things that are going to happen in this century that are going to make a discontinuity in the history of humanity. I think we're also inventing our successors. Okay, that we're inventing thinking machines. And this is, if it's true, some people would say, you're not going to ever invent a machine that can write the great American novel. And I was up at Stanford some time ago recently for some TV shoot, and the head of the artificial intelligence program at Stanford was in the room, and I just went up to him and I said, we could build a fully thinking machine by 2050. And he looked up at me and he said, yes. That was the extent of his answer. That was all the detail he felt was necessary. Okay. And let's say he's wrong and it's not by 2050, it's 2100 or 2150 or 2250. None of that matters. It's all short compared with these time scales. 1900, there you see Marconi there on the left, reading his stock quotes. By 1945, we had computers. I'm sure they took an entire room and all that, but the basic architecture was already there by the war. Right? Half a century, you go from inventing practical radio to inventing computers, and what these guys are saying is maybe by 2050 we have strong artificial intelligence, we have thinking machines. The point is that that's only a couple of centuries after you have the technology to make yourself visible to the point where you replace protoplasm with some sort of machine. Now, I know this doesn't sit well with many of you, but that's only because you're protoplasmic. The intelligent machines I talk to have no trouble with this idea. Okay. And by the way, the question is what happens to us afterward, but that's not the subject of this talk. And personally, I think all that will happen is that we will become their pets, which doesn't bother me so much because I'll get cat food, I get to sleep a lot. That's a good thing. All right. So all that is to say that once that happens, and I say it's going to happen soon, but you may disagree, then that changes everything, because now further evolution is no longer Darwinian. It's this is Darwinian evolution. Here's a horse 60 million years ago the size of a collie dog, and today most horses are the size of horses. Now, that took 60 million years. I had a personal computer in 77, it wasn't this one, but, and the one I have today is 10,000 times more powerful than the one I had in 77. 10,000 times better in, decades. So what happens is you invent a thinking machine, and the first thing you ask it is, hey, design something better than you are. And you build that. Hey, design something better than you are. You build that. Right? It doesn't take very long because whatever you're building, you're not even asking the question anymore. Okay? So once you build a thinking machine that's as clever as a human, within 20 years the machine is as clever as all humans put together. So this strikes me as so patently obvious and inevitable that I think you can forget that if we find ET in the next 20 years, which is more or less what I'm saying, then it'll be one of these soft, squishy little guys. It's not going to be anything like that. So I'm going to stop here and take some questions if you have them. Thank you. And silicon also has 4 covalent bonds like carbon does. But carbon is a smaller atom, so it's better at this. Okay. So you could say, all right, that it's very provincial to assume they'll be carbon-based, for example. Maybe it is, but it's not a terribly crazy idea. Maybe there's life that's totally different, but you don't know how to look for that. It's like saying, forget using radio, why don't you use hyperdimensional physics? Yeah, I get that all the time, because obviously the aliens are using it. Well, to me, it isn't obvious that they're using it, and secondly, if you don't know what it is, how can you possibly build any equipment to look for it? So it's the same sort of problem. You start with what you know, because at least you have something to go on. Yes, ma'am?
If I'm remembering properly, they used to be able to donate your own personal computer time when you weren't using it, and said you could look into it. Are they still doing anything like that to amplify your resources?
Yeah, she's asking the question, how can you participate in, there used to be something called SETI at Home, and there still is. SETI at Home still runs. That's not our project, it's great. The SETI Institute gets credit for SETI at Home, but it's in fact a UC Berkeley project. So it's good, you get the credit, you don't have to do the work. I recommend this. But yeah, SETI at Home is still running, and it's good. So a certain fraction of their data are distributed, and because there's so much compute power there, they're able to look for signal types that nobody else can really look for. So it's a good thing to do. We have our own participatory schemes called, what is it, SETI Live. You might look that up, where you use your eyeballs. You can see the guy with the big white hook is coming up here, so try to make it clear.
Has there been any serious look at binary stars? I know they aren't really good candidates for planets.
Yeah.
I would say in terms of space-based civilizations.
Yeah. Should we look at binary stars? Something like 55 or 60% of all stars have buddies. They're binary stars, or they're triple systems, and even more. Okay. And we used to throw all those out because we said, look, if you're on a planet going around a binary star system, you will very quickly get ejected. You'll just be kicked out because of the changing gravitational tugs on your planet. But it turns out that's not true in many cases. If you're far enough away from both stars, you'll be in a stable orbit. If you're in a close enough orbit to one or the other of the stars, you'll be in a stable orbit. And in fact, and as was pointed out, Nick Gautier, I think, did this, that I forget the number, but there are like a half a dozen or a dozen star systems, double star systems that have been found to have planets. So don't throw them out. I mean, it only increases the sample size by a factor of 2. And you've already heard me say that a factor of 2 is equal to a factor of 1. But it's there's no reason to rule out most binary stars. Okay.
Let's thank our speaker once more. Thank you.